Tonight, we're going to talk about the one rule in physics that almost every scientist agrees cannot be broken. A rule so fundamental that it shapes everything from how we understand time to whether humanity could ever reach another star. Light. You see it every morning. It comes through your windows. It reflects off surfaces. It carries the image of everything around you directly into your eyes. We take it completely for granted. But light has a speed, and that speed is not just a number in a textbook. It is the hardest wall in all of physics. The universe appears to be built around it. If you find comfort in these gentle explorations of space and science, I'd be grateful if you'd consider subscribing and giving this video a like. I'd love to know where you're watching from and what time it is for you. Feel free to drop your location and time in the comments below. The speed of light is 299,792 kilometers per second. In a single second, light can circle the entire Earth 7.5 times. It reaches us from the moon in just over a second. It takes about 8 minutes to travel from the surface of the sun to your eyes. When you look up at the night sky, every star you can see is so far away that its light left years, decades, sometimes thousands of years before it reached you. The universe is not just large, it is large in a way that makes light seem slow. And here is where the rule comes in. Einstein's special theory of relativity, published in 1905, established that the speed of light is not just fast. It is a limit. Nothing with mass can reach it. Nothing carrying information can exceed it. The closer you push an object toward the speed of light, the more energy it takes to accelerate it further, infinitely more energy to reach light speed itself. The universe doesn't just make it difficult to go faster than light, it makes it mathematically impossible for anything with mass to even arrive at that speed. For over a century, that rule has held. Every experiment, every measurement, every particle accelerator, every telescope has come back with the same answer: nothing beats light. Here's what most people don't realize. That rule doesn't just limit our technology, it limits our future as a civilization. The nearest star to our sun is about 4.37 light years away. That means even light, the fastest thing in the universe, takes more than 4 years to get there. Our fastest spacecraft would take thousands of years. The Milky Way itself is 100,000 light years across. Without a way past Einstein's speed limit, humanity is not just confined to our solar system for now. We may be confined to it permanently. Every other star, every other planet, every potentially living world in the galaxy sits behind a wall we don't know how to cross. That is what is actually at stake when physicists talk about faster-than-light travel. It's not about convenience. It's about whether we are permanently isolated in one small corner of a universe almost incomprehensibly vast. So when a headline appeared in April of 2026 saying that researchers had measured something moving faster than light, it landed differently than most science headlines do. This wasn't a theory. It wasn't a computer simulation. It was an experiment, a direct measurement, published in Nature, one of the most respected scientific journals in the world. The team was at the Technion, a research institute in Israel, and what they observed inside an atomically thin material were dark points within a light wave, moving at speeds that exceeded the speed of light. The news spread fast. The question spread faster. Does this mean Einstein was wrong? Does this mean the wall has a crack in it? Does this mean the nearest star is no longer permanently out of reach? Tonight, we're going to answer those questions carefully. We're going to start with what the speed of light actually is and why it functions as a limit. We're going to look at exactly what the 2026 researchers found and what was actually moving faster than light. We're going to trace the history of serious physics research into faster-than-light ideas, from tachyons to quantum entanglement to warp drives. And we're going to look at where that research stands right now and what the future of it might look like. Some of what we find is going to deflate the headline. Some of it is going to be more interesting than the headline. And when tonight is over, you'll have grasped this subject at a depth that most people never achieve. And in April of 2026, a team of researchers announced they had actually measured something moving faster than light. So the question we're going to spend tonight answering is this: what exactly did they find? Does it mean what it sounds like it means? And are we any closer to the stars? Let's start with what the speed of light actually is. Not as an abstract constant you see in equations, but as a physical reality that governs everything that moves through the universe. Light travels at 299,792 kilometers per second. That number is almost impossible to make feel real, so let's try to give it some shape. The Earth has a circumference of roughly 40,000 kilometers. In one single second, light travels far enough to circle the Earth 7.5 times. Not 7.5 times per minute, per second. 1 second. The time it takes you to blink, and light has already lapped the planet 7 times and started on its 8th pass. Now think about the Moon. The Moon sits about 384,000 kilometers away from Earth. It's the furthest place humans have ever physically traveled to. It took the Apollo astronauts 3 days to get there. Light makes that same trip in about 1.3 seconds. When you look up at the Moon on a clear night, you're not seeing it as it is right now. You're seeing it as it was 1.3 seconds ago. That's how far away it is, and that's how fast light moves. The Sun is much further. The average distance from Earth to the Sun is about 150 million kilometers. At the speed of light, that crossing takes approximately 8 minutes. When you look at the Sun, which you shouldn't do directly, you're not seeing it as it is at this moment. You're seeing it as it was 8 minutes ago. If the Sun simply vanished right now, we wouldn't know for 8 minutes. The sky would still be bright. Everything would still feel normal. And then the light would stop coming. That's what 299,792 kilometers per second actually means in the solar system. Stretch it further, and the numbers become harder to hold on to. Light takes about 4.2 years to reach us from Proxima Centauri, the nearest star beyond our Sun. Not 4.2 days, not 4.2 months, years. The light arriving in your eye right now from that star left before many people reading this were born. Everything you've ever seen from another star is history, not current events. Here's what most people don't realize about the speed of light. It isn't just a property of light. It's a property of the universe. It's the speed at which all electromagnetic waves travel through a vacuum. Not just visible light, but radio waves, X-rays, microwaves, gamma rays, ultraviolet. Every signal from every satellite, every image from every space telescope, every piece of information that has ever traveled across the cosmos without a physical carrier, all of it moves at exactly c, the same number, 299,792 kilometers per second, always, with no exceptions. This is where it starts to feel strange. You might expect that the speed of something would depend on how fast the source is moving. If you throw a baseball from a moving train, the ball moves faster relative to the ground than it would if you threw it from a platform. That's how speeds normally add up. But light doesn't behave that way. A laser fired from a spacecraft moving at half the speed of light doesn't emit light at 1.5 times c. The light still moves at exactly c. A star racing away from us at incredible speed still emits light that travels toward us at 299,792 kilometers per second. The speed of light is completely independent of the motion of the source. That's not intuitive. It took a long time for physicists to take this seriously, and when they did, everything changed. We didn't just stumble onto that value once and assume it was constant. Physicists have measured the speed of light for centuries, getting progressively more precise. Ole Römer made the first credible estimate in 1676 by studying the timing of Jupiter's moons. Léon Foucault refined it in the 1800s using rotating mirrors. By By the late 20th century, measurements had become so precise that scientists actually redefined the meter in terms of the speed of light. Since 1983, the speed of light has been fixed by definition at exactly 299,792,458 meters per second, and the meter is defined as the distance light travels in 1,299,792,458 meters per second, and the meter is defined as the distance light travels in 1,299,792,458 of a second. We stopped trying to measure c because our definition of length itself depends on it. The number is that reliable. What makes the constancy of light speed so significant is what it means about the universe we live in. It isn't simply that no engine has been powerful enough to push a vehicle past c. It isn't an engineering limitation waiting to be solved. The speed of light is woven into the mathematical structure of spacetime itself. It appears in Maxwell's equations, which describe electromagnetism. It appears in quantum mechanics. It appears in general relativity. Remove c from the equations of modern physics, and the equations stop working. The speed of light isn't a fact about photons. It's a fact about reality. Think about what that implies. When you see a flash of light, you're watching something that the universe has set a fundamental speed for, not arbitrarily, but because the geometry of space and time is structured in a way that demands it. Every photon, every radio wave, every beam of X-rays is moving at the one speed the geometry of the universe naturally produces for massless things traveling through a vacuum. That's not a coincidence. That's a deep feature of how the cosmos is built. And here's the thing, every time physicists have checked, under different conditions, in different media, with different instruments, the speed of light in a vacuum has come back the same. In glass, in water, in certain crystals, light slows down. But that's because light interacts with matter and gets absorbed and re-emitted as it passes through. In a vacuum, with nothing to interact with, it always returns to exactly c, always, without exception. Across every experiment conducted in the history of physics, we've tested the speed of light from every angle, in every medium, under every condition we can produce. And it never changes. Which means if you want to understand why faster than light travel seems impossible, you have to understand what Einstein figured out when he sat down and asked what that constancy really implies. Albert Einstein was 26 years old when he published his special theory of relativity in 1905, and the conclusion he reached wasn't that light is fast. Everyone already knew light was fast. What Einstein concluded was something far stranger, that the speed of light is the same for every observer, regardless of how fast that observer is moving. That single idea, that constancy, is what breaks everything you think you know about motion. Here's what makes that so strange. Imagine you're standing still and you throw a baseball at 60 miles per hour. Now imagine you throw that same baseball while running at 20 miles per hour. From the perspective of someone watching, the ball travels at 80 miles per hour. Speed adds. That's how motion works, and every human experience before Einstein confirmed it. Now imagine you're on a spacecraft moving at half the speed of light, and you shine a flashlight forward. How fast does that light travel? You would expect it to move at 1.5 times the speed of light, relative to a stationary observer. That's how the math should work, but it doesn't. The light still moves at exactly 299,792 kilometers per second, not 1 meter per second faster, not 1 meter per second slower, exactly c. Every observer, no matter their speed, measures the same value. Einstein didn't just suggest this. He built it into the foundation of physics as a postulate, a starting assumption from which everything else follows. And the consequences are extraordinary. If the speed of light is fixed, then other things must give way. Space and time themselves have to bend to make the numbers work. This is not metaphor. It is the literal structure of the universe. When an object moves faster, time for that object runs slower relative to a stationary observer. This is called time dilation. At everyday speeds, the effect is too small to notice, but as an object's velocity approaches the speed of light, the effect becomes dramatic. A clock moving at 90% of light speed ticks at less than half the rate of a stationary clock. At 99% of light speed, it ticks roughly 7 times slower. At 99.9%, more than 22 times slower. The closer you get to C, the more severely time stretches. Length contracts as well. An object moving at high speed appears compressed along the direction of travel from the perspective of a stationary observer. At 90% of light speed, an object is nearly half its rest length. At 99%, it's compressed to about 1/7. These effects aren't optical illusions. They're real physical consequences of the structure of spacetime. But here's where the speed limit truly comes from. As an object accelerates, its mass increases. This is the part that builds the wall. At rest, an object has what physicists call its rest mass. As its velocity increases, its relativistic mass grows. At 90% of light speed, the object's effective mass is roughly 2.3 times its rest mass. At 99%, it's about 7 times heavier. At 99.9%, more than 22 times. The pattern should be familiar because it mirrors the time dilation numbers exactly. That's not coincidence. It's the same underlying mathematics. Think about what mass increase means for acceleration. To accelerate an object, you need to apply force. The more massive an object, the more force it takes to accelerate it. As an object approaches light speed, it gets heavier, which means it needs more force to accelerate further, which means it gets even heavier, which means it needs still more force. The energy required doesn't just grow large, it approaches infinity. The universe demands infinite energy to push a massive object to self, and infinity is not a number you reach. It's a boundary you approach forever without arriving. This is what physicists mean when they call the speed of light a cosmic speed limit. It's not that we haven't built a fast enough engine. It's that the universe is structured so that a massive object can never reach that speed. Each increment of acceleration costs more than the last. The closer you are to C, the more impossibly expensive the next fraction of a percent becomes. And then there is E equals mc squared. Einstein published this separately, shortly after the special relativity paper, but it flows directly from the same mathematics. Energy and mass are not different things. They are the same thing, expressed in different forms. The c² factor, the speed of light multiplied by itself, is an enormous number, roughly 9 times 10 to the power of 16. This is why even a small amount of mass contains a staggering amount of energy. 1 gram of matter, fully converted, releases energy equivalent to roughly 21,000 tons of TNT. That equation governs nuclear reactors, nuclear weapons, stellar fusion, everything that converts mass into energy or energy into mass. For the speed limit, E equals mc squared matters because it confirms what the mass increase calculation implied. A massless object, like a photon, can travel at c precisely because it has no rest mass. It doesn't accumulate relativistic mass the way ordinary matter does. It simply travels at c, as it must because there is no other speed available to a massless particle. But give an object any rest mass at all, any mass whatsoever, and the equations guarantee it can never reach c. The energy cost becomes infinite before you arrive. Physicists tested these predictions almost immediately after 1905. Particle accelerators, which push electrons and protons to extraordinary velocities, confirmed every consequence of special relativity. Particles moving at 99.9999% of light speed behave exactly as the equations predict. They're enormously heavier. They experience dramatic time dilation, and they stubbornly refuse to reach C no matter how much energy gets pumped into them. Every test has confirmed the framework. Every single one. This is not a theory we're uncertain about. The mathematics and the measurements agree with extraordinary precision. So the wall is real. Not a barrier we haven't overcome yet. A barrier built into the architecture of spacetime. But here is the thing that physicists caught almost immediately. Read the equations carefully. They forbid a massive object from accelerating from below the speed of light up to the speed of light. They don't say anything about an object that was always traveling faster than light. The mathematics describes what happens as you approach C from below. It says nothing definitive about what happens above C. That gap is small. It's easy to miss if you read quickly. But physicists don't read quickly, and they noticed. What Einstein's equations actually say is that nothing starting below the speed of light can be accelerated up to it. And physicists noticed almost immediately that this leaves open a strange and uncomfortable question. What about something that was never below light speed to begin with? In April of 2026, a research team at the Technion in Israel published a paper in Nature that immediately generated headlines around the world. The claim was simple on its surface. Researchers had measured something moving faster than light, not in theory, not in a simulation, in a real laboratory with real instruments, producing real numbers that came back the same way every time they ran the test. Here's what most people don't realize about this experiment. It wasn't trying to build a spacecraft. It wasn't trying to send a message across the galaxy. The team was studying something called optical phase singularities. And if you haven't heard that term before, that's exactly where we need to start. Light is a wave, and like any wave, it has a phase, a way of describing where any given point on the wave sits in its cycle. Think of it like a clock face. At any moment, the wave is at some position in its repeating pattern. But there are special locations inside a light wave where that phase becomes completely undefined, where the wave's amplitude drops to zero. These are the dark points. They're not holes in the light exactly. They're more like the eye of a storm, a precise location where the wave structure wraps around a central point of nothingness. Physicists call them vortices. The wave spins around them, and at the very center, there is no wave at all, just darkness embedded inside the light field itself. These singularities were first predicted in the 1970s. Physicists working on wave optics recognized that the mathematics of wave interference required them to exist. If you have two waves crossing each other at the right angles, with the right phase relationships, you will always get points where the phases cancel completely. The math demanded it. But actually seeing one of these singularities move, tracking its velocity directly, was an entirely different challenge. The distances involved are measured in nanometers. The timescales involved are almost beyond description. The team at the Technion chose a material called hexagonal boron nitride. It's an atomically thin, two-dimensional crystal, a single layer of atoms arranged in a repeating hexagonal pattern, like a sheet of molecular chicken wire. Materials like this have become some of the most important tools in physics over the last decade. They're thin enough that light waves passing through them behave in ways that are much easier to control and measure than in bulk materials. The geometry is clean, the behavior is predictable, and crucially, the wave patterns that form inside hexagonal boron nitride were exactly the right environment for generating and tracking optical phase singularities. To capture what happened next, the team needed an instrument capable of operating at scales that feel almost fictional. They used a high-speed electron microscope with resolution sharp enough to record events unfolding over 3 quadrillionths of a second, 3 times 10 to the negative 15 seconds. To put that in perspective, 1 quadrillionth of a second is to 1 second what 1 second is to about 31 million years. The microscope was resolving time intervals at that scale. It was reading the geometry of a light field inside an atomically thin crystal, faster than almost anything in nature moves at all. The real challenge wasn't simply possessing a microscope of this caliber. It was isolating the specific effect they wanted to measure. Inside hexagonal boron nitride, light waves propagate through in complex patterns, with multiple interference effects occurring simultaneously across the crystal. The team needed to engineer precise conditions where optical phase singularities would form reliably and predictably, and where those singularities would move in a way that could be tracked consistently from one measurement to the next. They used specifically tuned incident light, carefully controlled polarization states, and exact angles of illumination to create the conditions they needed. Even with all these experimental controls in place, the phenomenon remained fragile and sensitive to disturbance. A slight variation in the crystal's temperature could affect the results measurably. Contamination on the surface could scatter light in unpredictable ways. The researchers had to work under conditions of extreme isolation and precision. Every measurement had to be performed in a carefully controlled environment, with multiple redundancy systems built in to ensure that what they were measuring was genuine and not an artifact of their measurement apparatus. This obsessive attention to detail would become crucial when other physicists began asking whether the team had actually measured what they claimed to have measured. But even that instrument couldn't capture everything in a single shot. The singularities moved too fast. The events were too brief. So the team developed a different approach. They ran the experiment not once, but hundreds of times. Each run was identical, except for one thing. The timing of the measurement was offset by a tiny delay compared to the previous run, a few quadrillionths of a second later each time. Then they took all those hundreds of images and stacked them together in sequence. What emerged was a time-lapse, a frame-by-frame reconstruction of the singularities as they formed, moved, and collided. What they saw was extraordinary. The dark points didn't drift. They moved with purpose. The vortices tracked across the material, hurtling toward each other at velocities the team could measure directly from the position data. And as the singularities approached each other, something happened. They annihilated. Two dark points colliding and canceling each other out, the vortex structure unwinding in an instant. In the moments just before that annihilation, as the singularities closed the distance between them, their measured velocities exceeded the speed of light. Not by a small margin. The numbers were unambiguous. This was superluminal motion, directly observed, with measurements precise enough to rule out instrument error or statistical noise. The team checked their results. They rechecked them. The singularities had moved faster than light, a prediction that physicists had made roughly 50 years earlier, sitting in journal papers and theoretical frameworks that most people had never heard of, had just been confirmed by direct experiment inside a crystal thinner than a single cell. The physics community knew what this finding meant in technical terms. The researchers knew what it meant, but when the paper hit the public, the framing was almost impossible to resist. Something moved faster than light. The speed limit appeared broken. The headlines spread fast. And for most readers, the natural conclusion was obvious. Einstein was wrong. There's a reason this result felt so electric. For decades, faster-than-light motion had been treated as firmly in the category of science fiction. Every serious physicist would tell you that Einstein's special theory of relativity makes it impossible. You cannot accelerate a massive object to light speed. You cannot send information faster than light. The rule was presented as airtight. And now a peer-reviewed paper in Nature was reporting measurements of something moving faster than light inside a real laboratory, using a real experiment that other researchers could verify. That's not a thought experiment. That's not a theoretical loophole. That's data. The question of what it actually means, whether it breaks relativity, whether it opens any door to faster-than-light travel, whether Einstein's framework needs to be revised, that's where the story gets more complicated. And that's exactly what we're going to work through next. But the discovery itself deserves to be appreciated on its own terms first. This was decades of theoretical prediction finally meeting experimental confirmation. A team of physicists built an instrument that could resolve 3 quadrillionths of a second, ran an experiment hundreds of times, stacked the results into a coherent picture, and measured velocities that exceeded the speed of light directly and unambiguously. That is a genuine scientific achievement, regardless of what it does or doesn't mean for warp drives. The measurement was unambiguous. These dark points, these phase singularities, had moved faster than light, confirming a prediction that had sat in physics papers for roughly half a century. And the question everyone immediately asked was the same one you're probably asking right now. Does this mean Einstein was wrong? So here's the thing that separates this discovery from everything you might have imagined when you first heard the headline. When researchers at the Technion measured those dark points moving faster than light, they weren't watching a particle break the speed limit. They weren't watching energy outrun a photon. They weren't watching any physical object cross the universe at impossible speed. What they were watching was a geometric feature of a wave, a location, a pattern, a shape, and that is an entirely different category of thing. Most people don't realize that distinction exists. Most people don't realize it matters enormously, but it is the entire foundation of what that experiment actually showed. And without understanding it, you can't understand what the result means. Let's start with what a phase singularity actually is. A wave has a phase. Think of a wave on the ocean. At any given point on the water, the surface is either rising or falling, and you can describe exactly where in the cycle that point sits. The phase is just that, a description of where in the cycle you are at a particular location. But inside a complex wave field, there are points where the phase becomes undefined, points where the wave's amplitude drops to exactly zero, where there is no wave, only silence, only darkness. At those points, the very concept of phase breaks down. There's nothing there to measure. These are the singularities. They're not particles. They're not energy concentrations. They're locations in the wave field where the mathematics of the wave become undefined, like the exact center of a whirlpool. Think about that whirlpool. Water is spinning around a central point. Every molecule of water in that whirlpool is moving, circling, churning, following the flow. But the center itself, the exact middle of the vortex, is a location, not a thing. It's the point where the water can't decide which direction to flow. Now, if the entire whirlpool drifts across the surface of a lake, that center point moves too. And in principle, that center can move at any speed at all, faster than any individual water molecule, faster than the current that created it. No water is traveling at that speed. No mass is moving at that speed. A geometric point is shifting its location, and geometric points have no speed limit. Here's another way to see it. Take a very long pair of scissors. Hold them open. Now close them slowly. The point where the blades cross, the intersection point, moves along the blades as you close them. If the scissors are long enough and you close them fast enough, that intersection point can travel down the blades faster than your hands are actually moving. Not faster than the speed of light, not in a household pair of scissors, but the principle holds. The intersection point is not a thing. It is a location defined by the geometry of the two blades. It carries no mass. It transfers no energy from one end of the scissors to the other. It is purely a consequence of shape. You could make it move at any speed you wanted, simply by changing the geometry of the blades, and nothing physical would be traveling at that speed. The same logic applies to a laser pointer and the moon. If you point a laser at the lunar surface and rotate your wrist quickly enough, the dot of light sweeping across the moon's surface can move faster than light. Not the photons. The photons are traveling at exactly the speed of light, every one of them. But the dot, the location on the moon's surface where the photons happen to be arriving, can sweep sideways at superluminal speed. The dot isn't a physical object. It's a pattern defined by geometry. No photon is outrunning any other photon. You couldn't use that sweeping dot to send a message to someone standing on the moon, because the dot has no memory, no structure, no ability to carry information from one location to another. It's just a moving point of brightness, defined entirely by where you're pointing. The 2026 phase singularities work the same way. They are dark points, points of zero amplitude, embedded in the geometry of a light wave inside hexagonal boron nitride. As the wave evolves, as the interference pattern shifts and the vortex structure changes, those points of darkness relocate. Their location moves. That location, that geometric feature, moved faster than light. But here's what didn't happen. No photon moved faster than light. No electron moved faster than light. No piece of information encoded in the wave was transmitted faster than light. The singularity is not a carrier of anything. It's more like the eye of a storm than the storm itself. You can track where the eye is. You can watch it move. But the eye is not a thing traveling through space. It's a location defined by the surrounding structure. Einstein's speed limit, the one that makes faster than light travel so difficult, applies to three specific categories: mass, energy, information. Those are the things the universe protects with the speed of light. Those are the things that, when they approach light speed, experience time dilation and length contraction and infinitely increasing resistance. Those are the things that can never, in standard physics, actually reach C. Phase singularities are none of those things. They have no mass. They carry no energy from point to point. They transmit no information. There is no way to encode a message in a moving singularity and have it received at a distant location before light could carry it there. The physics simply doesn't work that way. The singularity moves, yes, but nothing moves with it. This is not a loophole physicists invented after the fact to protect Einstein's reputation. This distinction has been understood for decades. The prediction that phase singularities could move superluminally dates back to the 1970s, half a century before the Technion experiment confirmed it. What the 2026 experiment did was observe it directly, measure it precisely, and show that the phenomenon is real in a physical material, not just in abstract mathematics. That matters enormously for reasons we'll get to. But it does not mean the speed of light has been broken in the sense that popular coverage implied. No mass moved faster than light. No energy moved faster than light. No signal or message or piece of information moved faster than light. What moved faster than light was a geometric feature, a location of darkness defined by the shape of a wave. And that distinction is not a technicality. It is the entire ballgame. Now, it would be easy to walk away from that explanation feeling like someone punctured a balloon, that the headline wrote a check the physics couldn't cash. And in a narrow sense, that's fair. No warp drive was built. No spacecraft moved faster than light. No message was transmitted instantaneously across the galaxy. The singularities that moved at superluminal speed carried no mass. They carried no energy. They carried no information. So it's reasonable to ask whether any of this actually matters. Here's what most people don't realize. The 2026 experiment wasn't a failed announcement of faster-than-light travel. It was the first time in history that superluminal phase singularity motion had ever been directly measured. Physicists had predicted this phenomenon since the 1970s. For 50 years, it lived in theoretical papers. Nobody had seen it. Now they had. That's not a small thing. Think about what it means to confirm a 50-year-old prediction through direct observation. This wasn't a computer model. It wasn't a mathematical argument. It was a real measurement inside a real material, recorded by a real instrument. The researchers used hexagonal boron nitride, an atomically thin two-dimensional material. They used an electron microscope with a time resolution of 3 quadrillionths of a second. They ran the experiment hundreds of times. They stacked the images into a time lapse, and the singularities moved faster than light every time. The prediction was right, and when a 50-year prediction turns out to be exactly right, that tells you something important about the quality of the theoretical framework that generated it. The technique itself is worth dwelling on. The team's method, electron interferometry, is now a demonstrated tool for studying phenomena at the nanoscale in quantum materials. Before this experiment, researchers had limited ways to probe the delicate internal wave structure of two-dimensional materials in real time. Now they have one more. That has immediate applications. Superconductors, for instance, involve wave phenomena that are extraordinarily difficult to observe directly. The same applies to certain fluid systems, to acoustic wave behavior, to photonic crystals. The laws governing how phase singularities move and interact appear across all of these systems. They're not exotic exceptions. They're a feature of wave physics in general. What this experiment did was give physicists a new window into that universal behavior. Here's another way to think about it. Imagine you've been told your entire life that there's a wall at the end of a particular road. You've never walked that road. You've been told about the wall by people who derived its existence from mathematics. For 50 years, everyone who studied the math agreed the wall was there. Then someone finally walks the road, reaches the end, and reports back. The wall is there, exactly where the math said it would be. That's not a disappointment. That's confirmation that the map is accurate. And an accurate map is how you plan every journey that comes after. Physics advances by finding exactly where rules apply and where they don't. That's not a poetic observation. It's a description of how the discipline actually works. Quantum mechanics didn't emerge because someone sat down and invented it from scratch. It emerged because experiments kept showing that classical physics was failing at very small scales. The failures were precise and reproducible. Scientists mapped the boundaries of classical physics until those boundaries were clear enough that a new framework became necessary. The 2026 experiment contributes to the same kind of boundary mapping. It demonstrates with direct measurement that Einstein's speed limit applies to matter, to energy, and to information, but that the geometric features of wave systems can behave differently. That's a precise statement. Before the experiment, it was a theoretical statement. Now it's an empirical one. There's something worth understanding about how knowledge accumulates in physics. Theoretical predictions don't become facts the moment they're published. They become candidates. They stay candidates until experiments confirm or deny them. Some candidates wait decades, some wait a century. The photoelectric effect was predicted by Einstein in 1905 and experimentally confirmed in detail over the following years. Gravitational waves were predicted by the same paper trail of general relativity and confirmed in 2015, 100 years later. The detection of the Higgs boson came nearly 50 years after theorists predicted it. Superluminal phase singularity motion waited roughly half a century. The confirmation doesn't change the physics retroactively, but it changes our confidence in the framework that predicted it. And that confidence is what allows physicists to keep building on the framework without constantly doubting its foundations. So, what does the 2026 discovery actually tell us about faster-than-light travel? It tells us that the universe is not uniformly restricted. Certain things without mass, without energy, without information content, can move faster than light because Einstein's equations never applied to them in the first place. The speed limit is real. It's precise. It holds everywhere it's supposed to hold, but it doesn't hold everywhere. That distinction is now experimentally established, not merely theorized. And knowing precisely where a rule applies is fundamentally different from assuming it applies everywhere. Finding the exact edges of a rule is how you eventually find the loopholes. And the physicists who built the theory of warp drives weren't chasing science fiction. They were doing exactly the same thing, looking very carefully at what Einstein's equations actually forbid and what they, perhaps surprisingly, do not. The idea of traveling faster than light didn't begin with science fiction writers. It began with physicists who read Einstein's papers very carefully and started asking uncomfortable questions almost immediately. Einstein published Special Relativity in 1905. Within a few years, physicists were already probing its edges. The equations had a specific structure. They forbade something with mass from accelerating to reach light speed. But some researchers noticed that the equations didn't explicitly say what would happen on the other side of that wall. They said you couldn't cross it. They were quiet about what lay beyond it. That silence became an invitation. For most of the 20th century, faster-than-light ideas lived in two places at once. They lived in science fiction, in pulp magazines, and eventually in films and television. And they lived quietly in the margins of serious physics papers. Occasionally, those two worlds touched, but for decades they were mostly separate. Physicists who raised the question professionally risked being grouped with the science fiction crowd. That social pressure kept the subject at the edges of mainstream research for a long time, but it never disappeared entirely. In 1935, Einstein himself, working with Nathan Rosen, described a mathematical structure connecting two distant regions of spacetime. They weren't proposing a travel method. They were studying the geometry of general relativity. What they found was a bridge, a tunnel through the fabric of spacetime that the equations permitted to exist. The physics community filed it away. It was mathematically valid. It was probably not physical. And there it sat for decades. The question of negative energy emerged from a different direction. Physicists studying quantum mechanics began noticing that the vacuum of space was not truly empty. Quantum fluctuations meant that even in a perfect vacuum, energy was constantly appearing and disappearing on extremely small scales. In 1948, a Dutch physicist named Hendrik Casimir predicted that two uncharged metal plates placed very close together in a vacuum would experience a tiny attractive force. The reason was that quantum fluctuations outside the plates outnumbered those between them, creating a measurable pressure difference. That narrow region between the plates represented something extraordinary, a zone of negative energy density. Experimentally confirmed decades later, the Casimir effect became the only known real-world demonstration that negative energy could exist. The amounts were incredibly small, but the principle was there. Then, in 1967, Gerald Feinberg published a paper that changed the conversation. Feinberg was a professor at Columbia University, not a fringe figure, not an amateur enthusiast. He had read Einstein's equations carefully, the same way physicists had been doing for 60 years, and he noticed the same gap. The equations forbade accelerating a massive object to light speed. They said nothing about a particle that started out already moving faster than light. He called these hypothetical particles tachyons, from the Greek word for swift. He laid out their properties mathematically. They would have imaginary mass. They would slow down as they gained energy. They would speed up as they lost it. At light speed, their energy would be infinite, the precise mirror image of ordinary matter. Feinberg was careful. He didn't claim tachyons existed. He claimed the equations didn't forbid them from existing, and that this distinction was worth examining. The physics community's response was complicated. Some physicists engaged with the idea seriously. Others pointed out that tachyons, if they could carry information, would threaten causality in deeply uncomfortable ways. The argument was technical but devastating. Under certain conditions, a tachyon signal could arrive before it was sent, creating logical contradictions that seemed to undermine the foundations of physics itself. Tachyons never moved from theoretical curiosity to confirmed reality. But Feinberg's paper opened a door. It established that faster-than-light physics was a legitimate topic for professional physicists, not just screenwriters. Throughout the 1970s and 1980s, the EPR paradox and quantum entanglement added another layer. Einstein had identified in 1935 that quantum mechanics seemed to permit instantaneous correlations between distant particles, what he called spooky action at a distance. Experiments eventually confirmed that entanglement was real. Physicists spent years debating whether it could be used to transmit information faster than light. The consensus answer was no. But the process of reaching that answer required extremely careful thinking about what information actually means and how measurement works. That careful thinking produced real physics. By the early 1990s, the accumulated weight of these ideas had shifted something. Negative energy was real, even if tiny. Entanglement was real. The Einstein-Rosen bridge was mathematically valid. Tachyons were undetected but not obviously impossible. Physicists had spent decades mapping the edges of what relativity permitted and what it didn't, and the map was more complicated than the simple version said. The question wasn't settled. It was, if anything, more open than before. The most serious of those ideas, the one that genuinely changed how physicists think about what might be possible, came in 1994 from a Mexican physicist named Miguel Alcubierre. And what he proposed was so clever and so strange that it took years before people were sure it was even worth taking seriously. Gerald Feinberg was a physicist at Columbia University, and in 1967 he published a paper pointing out something that had apparently been hiding in Einstein's equations all along. Einstein's relativity doesn't actually forbid faster-than-light particles. What it forbids is taking a particle that starts below the speed of light and accelerating it up to reach that speed. Those are two different statements. Most people treat them as the same. Feinberg noticed they weren't. If a particle was never below light speed to begin with, if it was born already moving faster than light, then relativity has nothing to say against it. The equations permit it. Nobody had taken that seriously before. Feinberg did, and he gave these hypothetical particles a name: tachyons. The word comes from the Greek word for swift, and tachyons would be swift in a way that makes ordinary matter look stationary. A tachyon would always move faster than light. It couldn't slow down to light speed, just as ordinary matter can't speed up to reach it. Light speed would be the barrier from both sides. Ordinary matter approaches it from below and can never cross. Tachyons would exist entirely above it and could never fall back down. Here's where things get strange. The math that describes tachyons requires them to have what physicists call imaginary mass. Not imaginary in the everyday sense of made up. Imaginary in the mathematical sense. Mass expressed as the square root of a negative number. In most contexts, getting a square root of a negative number out of an equation is a signal that something has gone wrong. But in physics, imaginary quantities appear in real, meaningful situations. They often signal that a system is in an unstable regime, or that it's crossing some kind of boundary. For tachyons, imaginary mass is just how the algebra works out if a particle lives permanently on the far side of light speed. It's strange, but it's not necessarily nonsense. The behavior of tachyons would be the reverse of ordinary matter in almost every way. Normal matter gains energy as it speeds up. To push something faster, you add energy, and it accelerates. A tachyon works backwards. When you add energy to a tachyon, it slows down. When it loses energy, it speeds up. At the absolute minimum, a tachyon with zero energy would be moving at infinite speed, everywhere and nowhere simultaneously. To bring a tachyon down to exactly light speed would require infinite energy, just as it would require infinite energy to push ordinary matter up to light speed from below. The symmetry is almost elegant. Two regimes separated by an infinite barrier, each a mirror of the other. But there's a problem, a serious one. If tachyons can carry information, and any real particle interacting with other particles would carry information of some kind, then the causality of the universe breaks down. Here's why. Special relativity tells us that simultaneity is relative. Two events that happen at the same time for one observer can happen in a different order for an observer moving at a different velocity. That's not a minor technical detail. It's fundamental. Now take a tachyon signal. An observer sends a message using tachyons at faster than light speed. For a different observer moving in the right direction at the right velocity, that message arrives before it was sent. That observer can then send a tachyon response back. Under the right conditions, the response arrives at the original sender before they ever transmitted the first message. The sender can then decide not to send it. The message was never sent, but its effects already exist. That's a contradiction, not a paradox you can resolve with clever reasoning. A genuine logical collapse. Cause and effect stop working. This is the problem that has haunted tachyon physics since Feinberg's paper. You can write down the equations. The particles are internally consistent. But the moment they interact with anything, the moment they carry even a single bit of information from one place to another, you get situations where effects precede causes. And a universe where effects can precede their causes is not a universe that can be coherently described. Everything we know about how reality works depends on causes coming first. Physicists have spent decades trying to find a version of tachyon theory that avoids this. Some have argued that the way tachyons couple to other particles would naturally prevent them from transmitting information in any usable way. Others have proposed interpretations where the causality violation is more subtle and might not produce true contradictions in practice. A paper published in Physical Review D in 2024 argued that most of the standard objections to tachyon physics had been built on assumptions that weren't actually necessary. The authors introduced what they called the inverse principle, and under that framework, they claimed the causality problems could largely be resolved. The paper attracted attention. It hasn't settled the debate. No experiment has ever detected a tachyon. Physicists have looked. High-energy collisions at CERN's Large Hadron Collider have generated conditions far beyond anything in ordinary physics, and nothing moving faster than light has ever appeared in the data. Cosmic ray experiments, precision measurements in particle physics, searches for anomalous signals in neutrino experiments, none of it has turned up a tachyon. There's no track in a detector, no anomalous energy signature, nothing. What has emerged more recently is the idea of tachyon-like quasi-particles. Not real particles traveling through the vacuum, but particle-like excitations in certain materials that behave mathematically like tachyons. These are similar to other quasi-particles like phonons and polaritons that appear in solid-state physics. In laser-like media, theorists have predicted that excitations exist which move faster than light within the material and obey something resembling tachyon equations. This is different from a real black hole, but it gives physicists a place to study the mathematics in a controlled setting. There's also a speculative proposal, still unreviewed and highly controversial, that tachyons might not just be rare curiosities, but might actually dominate the composition of the universe. The proposal attempts to use tachyons to explain dark matter and dark energy, the two enormous mysteries that account for most of what the universe is made of. The model reportedly fits observational data on the large-scale structure of the universe surprisingly well. Most physicists are skeptical, deeply skeptical, but the fact that a tachyon cosmology can be written down at all and not immediately contradict what we observe says something about how unresolved these questions still are. No experiment has ever detected a tachyon, and most physicists treat them as a mathematical curiosity rather than a real feature of nature, but they've never quite gone away, and the theoretical machinery built around them has started generating predictions that look, at least superficially, like they might be testable. Of all the ideas people have proposed for sneaking around Einstein's speed limit, the one that gets the most attention and causes the most confusion is quantum entanglement. It shows up everywhere. Popular science articles invoke it. Science fiction builds entire faster-than-light communication systems around it. And people who have just learned about quantum mechanics almost always arrive at the same question. If measuring one particle instantly affects another particle on the other side of the galaxy, doesn't that mean something traveled faster than light? It seems obvious. It seems like it has to mean that. Here's what most people don't realize. It doesn't. And understanding why requires understanding what entanglement actually is. When two particles become entangled, they share a single quantum state. You can't describe one of them independently of the other. They're bound together by the mathematics of quantum mechanics in a way that has no equivalent in everyday experience. Measure one particle's spin and find it pointing up. The other particle, no matter where it is, will instantly have a spin pointing down. Not because a signal traveled between them, not because one particle told the other what to do. The correlation exists the moment you measure, regardless of the distance. A meter, a kilometer, across a galaxy. It doesn't matter. Einstein hated this. He called it spooky action at a distance. He was convinced it couldn't be real, that quantum mechanics must be missing something, some hidden variable that explained the correlations without requiring instantaneous influence across space. For decades, physicists argued about it. Then in 1964, a physicist named John Bell worked out a mathematical test. He showed that if hidden variables were responsible for the correlations, the measurement results would have to obey certain statistical limits. Real entanglement would violate those limits. Experiments starting in the 1970s and continuing through increasingly precise tests over the following decades kept checking. Entanglement violated Bell's limits every time. The correlations were real. Spooky action at a distance was not a gap in the theory. It was a feature of reality. So the correlations are genuine. They appear instantaneously. Why can't we use them to send a message faster than light? Here's the problem. When you measure your particle, you don't get to choose what result you get. The outcome is random. Spin up or spin down. Quantum mechanics gives you probabilities, not control. You can know that if you measure spin up, the distant particle will be spin down. But you can't force your particle to be spin up. You can't encode a message in the outcome of a quantum measurement because the outcome isn't yours to control. The distant observer measures their particle too. They get a random result. They see spin up sometimes and spin down sometimes. From their perspective, the results look completely random. They have no idea whether the correlations exist until you contact them through ordinary communication and compare notes. That comparison, the step where you actually learn whether your measurements were correlated, has to travel through space the conventional way. A radio signal, a light pulse, something limited to the speed of light. Think about what that means. The entanglement happens instantaneously. The correlation is real. But the information that would let you use that correlation is stuck behind the same old speed limit as everything else. Physicists have tried to find workarounds. For decades, researchers have devised clever schemes. What if you measured the particles in a particular sequence? What if you used multiple entangled pairs? What if you made measurements on one side that seemed like they should tell the other side something before any conventional signal arrived? Every scheme has failed, not just failed in practice, failed in principle. Physicists eventually proved this rigorously. The result is called the no communication theorem, and it demonstrates that quantum mechanics itself, at a fundamental level, prevents entanglement from transmitting information. The key is something called the no cloning theorem, which says you cannot make a perfect copy of an unknown quantum state. If you could clone quantum states, you might find ways to extract more information from entangled particles and use that information for signaling. The fact that you can't is not accidental. It turns out to be deeply connected to the structure of quantum mechanics as a whole. The same mathematics that produces entanglement also prevents you from exploiting it as a communication channel. The two features, the spooky correlations and the inability to use them, come from the same place. This is one of the stranger aspects of quantum mechanics. It gives you something that looks like instantaneous connection across arbitrary distances. It gives you correlations that cannot be explained by anything traveling between the particles at the speed of light. And then it refuses to let you use any of that for communication. The universe appears to have designed the loophole and sealed it shut at the same time. None of this means entanglement is useless. Quantum cryptography uses entanglement to build communication systems that are secure against eavesdropping in a way classical systems cannot match. Quantum computing uses entanglement to perform certain calculations at speeds impossible for ordinary computers. Quantum teleportation, which, despite the name, is not transportation, uses entanglement to transfer quantum states between particles. These applications are real, they are growing, and some of them are already in use, but none of them transmit information faster than light. All of them still require a conventional communication channel somewhere in the process. Here's what's genuinely strange about all this. Entanglement is one of the most tested phenomena in modern physics. It is also one of the least understood at a deep level. Physicists know how to calculate with it. They know what it predicts. They don't fully agree on what it means, on what is actually happening between those two distant particles when one is measured and the other instantly responds. Different interpretations of quantum mechanics give different answers to that question. What they all agree on is the practical consequence. No information gets through faster than light. Every physicist who has ever tried to find a way around the no communication theorem has failed. And it hasn't just failed experimentally, it's been proven mathematically that it cannot work, which means the fastest any information can travel through the universe is still the speed of light. And entanglement, for all its genuine strangeness, does not change that. In 1994, a Mexican theoretical physicist named Miguel Alcubierre was watching Star Trek and wondering whether anything in Einstein's general relativity actually forbade what the show was depicting. That's not a simplified version of the story. That's what actually happened. Alcubierre was a graduate student at the time, and he sat down and asked a question that sounds almost too simple. Does general relativity actually say a warp drive is impossible? Not whether we could build one, not whether we had the materials, whether the physics as written ruled it out entirely. What he found surprised him. It surprised a lot of people. Here's the key insight, and it's worth slowing down to understand it properly. Einstein's equations say that no object can move through space faster than light. That's the rule. That's the wall. But those same equations say nothing about how fast space itself can move. And that's a completely different thing. Space is not an object. It doesn't have mass. It doesn't carry information from one place to another in the way a signal does. And there is nothing in general relativity that prevents space from moving faster than light. We actually have evidence that this happens. In the earliest moments after the Big Bang, during a period cosmologists call inflation, the universe expanded so rapidly that regions of space were moving apart faster than light could cross between them. They weren't violating relativity. Space itself was stretching, and the speed of that stretching had no upper limit. The galaxies sitting in that space weren't moving faster than light through their local region. The region was just growing. That's a distinction that sounds subtle, but it's physically real, and it's the foundation of everything Alcubierre built. This was the conceptual breakthrough that Alcubierre seized upon. If inflation had done it in the early universe, what prevented the same mechanism from being engineered artificially? The universe itself had demonstrated that space-time could be shaped and manipulated on cosmic scales. The question wasn't whether such deformations violated fundamental laws. The question was whether a clever enough physicist could design one deliberately. Alcubierre realized that the barrier wasn't physics, it was engineering. What Alcubierre proposed was this. Imagine a spacecraft sitting inside a bubble of flat, undisturbed space-time. Around that bubble, you engineer a specific configuration of space-time geometry. In front of the craft, space expands. The bubble, and everything inside it, gets carried along by this wave of space-time deformation, like a surfer riding a swell. The surfer doesn't swim faster than the wave. The surfer just sits on it and gets moved. Alcubierre's spacecraft doesn't accelerate through space in the conventional sense. It sits still inside its bubble, while the geometry of space itself does all the work. This is the crucial point where the Alcubierre drive escapes the conventional limits of physics. A spacecraft accelerating through space is fundamentally constrained by the speed of light. But a spacecraft sitting motionless inside a bubble, whose bubble is carried by space-time deformation, isn't accelerating at all. There's no rocket pushing it. There's no G-force pressing the occupants against the seats. The bubble itself is the only thing moving, and there's nothing that says a geometric distortion in spacetime can't propagate at any speed whatsoever. Think about what that means for relativity. Inside the bubble, physics works exactly as it always does. The occupants of the spacecraft experience no unusual forces. They're not being accelerated. They're not in a high-gravity environment. From their perspective, they're sitting in a perfectly ordinary region of spacetime. The speed of light inside the bubble is still the speed of light. Nothing inside has moved faster than light. But from outside, from the perspective of someone watching the bubble travel across space, the craft has covered a distance faster than light could have covered it by traveling through the undisturbed space-time between the 2 points. The shortcut isn't through space, it's in the shape of space. This is what made the proposal so remarkable and so troubling in equal measure. The people inside the bubble would experience no sensation of movement. They would measure no strange effects. If they looked at a clock and a light beam, they would see the light beam moving at the standard speed of light, exactly as relativity demands. But somehow, mysteriously, they would arrive at a destination that lay light years away. The journey would take less time than the light itself would require to cover the same distance in normal space. Alcubierre published this in the journal Classical and Quantum Gravity. That matters. This wasn't a blog post or a magazine article or a press release. Classical and Quantum Gravity is one of the central peer-reviewed journals in theoretical physics. It was reviewed by relativists, people who spend their careers working with Einstein's field equations, and they found that the mathematics was sound, not speculative, not an approximation. Alcubierre had written down an exact solution to Einstein's equations, a metric in the technical language of general relativity, describing a configuration of space-time that would move a region of space along a chosen path at any speed desired, including speeds greater than light. The reason relativists took it seriously is worth understanding. When you're working in general relativity, you're working with equations that describe how the geometry of space-time responds to the distribution of mass and energy. Those equations have many solutions. Some of them describe black holes. Some describe the expanding universe. Some describe hypothetical objects we've never observed. But the equations don't know or care whether a solution is physically realizable. They just describe what would happen if a particular geometry existed. Alcubierre had found a geometry. The question of whether nature permits that geometry to actually form is a separate question entirely, and it's the harder one. The geometry of the warp bubble is specific and unusual. The spacecraft sits at the center of what looks, in the mathematics, like a kind of distortion ring. The region ahead of the craft has compressed space-time, so points that were far away become effectively closer. The region behind has expanded space-time, so the space the craft already occupied stretches out behind it. The craft isn't falling through a tunnel, it's riding a shape. The bubble moves. The craft, relative to its immediate surroundings, is essentially stationary. There's something elegant about this that goes beyond the engineering fantasy. Alcubierre's solution is genuinely beautiful in the way that a clever proof in mathematics is beautiful. It takes a constraint, the speed of light, and finds a structure that doesn't break the constraint but sidesteps it entirely, using the geometry of space-time rather than velocity through space-time. It respects every rule Einstein wrote. It violates none of them. It just uses them in a way nobody had written down before. The spacecraft itself doesn't need conventional thrust. There's no rocket equation to satisfy, no fuel mass to calculate. The bubble is not a propulsion system in the sense we normally mean. It's a reshaping of the space around the craft. You don't push the craft forward. You change what forward means, geometrically speaking, and the craft arrives without ever having moved through the space it crossed. Whether that distinction feels real or philosophical depends on how you think about space. But in general relativity, it's not philosophical at all. Space has geometry. Geometry can change, and if geometry changes the right way, everything inside it goes along for the ride. Physicists who reviewed the paper came away with a consistent reaction. The math worked. The solution was real. It was legitimate general relativity, correctly applied, yielding a result that nobody had found before. And almost immediately after confirming it worked, they started calculating what it would take to actually build it. What kind of energy would be needed? What kind of matter would produce the required spacetime geometry? Whether any of the required materials could exist in nature. Those calculations did not go well. The Alcubierre drive was real mathematics applied to real physics. The solution genuinely exists within general relativity's equations, but it came with a price tag so enormous that when physicists first calculated it, they couldn't decide whether to be more impressed that it worked or more despairing that it would never be built. The Alcubierre drive works on paper, but building it requires something that, as far as anyone knows, may not exist in the universe in the quantities needed. That something is called exotic matter, not antimatter, not dark matter, not some exotic element on a periodic table we haven't filled in yet. Exotic matter, in the technical sense physicists use when they talk about warp drives, means material with negative energy density. That distinction matters enormously. Regular matter, every atom in your body, every planet, every star, curves spacetime inward. It creates gravity wells. Things fall toward it. That's what mass does in general relativity. It bends spacetime, and that bending pulls other things in. Exotic matter would do the opposite. It would curve spacetime outward. It would repel rather than attract. It would create, in effect, a region of anti-gravity. Here's what that means for the warp drive. Alcubierre's design needs the space in front of the bubble to contract, and the space behind it to expand. Contracting space in front requires negative energy density. Something has to push spacetime in the wrong direction. Without exotic matter, you can't build the front half of the warp field. The geometry collapses. The whole mechanism fails. Exotic matter isn't a minor engineering challenge buried somewhere in the design. It is the design. You can't substitute anything else and get the same result. So does exotic matter exist? Here's what most people don't realize. There is one experimentally confirmed phenomenon that produces a region of negative energy density. It's called the Casimir effect. If you take two metal plates and place them extremely close together in a vacuum, we're talking gaps measured in nanometers, something strange happens. The plates attract each other even though there's nothing between them. The reason is quantum mechanics. The vacuum isn't empty. It's filled with fluctuating quantum fields, and those fluctuations come in different wavelengths. Between the plates, only fluctuations small enough to fit in the gap are permitted. Outside the plates, all wavelengths are present. That imbalance means there's more energy outside the plates than between them. The region between the plates has lower energy than the surrounding vacuum, lower than zero. Negative energy density. The Casimir effect is real. It's been measured. It's been confirmed in laboratories around the world. It's not theoretical. There is a genuine, physically observed region of negative energy density between those plates. But here's the problem. The amount of negative energy the Casimir effect produces is almost beyond description in how tiny it is. We're talking about a force so weak it took extraordinarily sensitive equipment to measure in the first place. To use Casimir effect negative energy to power a warp bubble would be like trying to run an entire city off a single spark of static electricity. The scales don't just mismatch, they don't exist in the same universe of possibility. When physicists first sat down to calculate how much exotic matter the Alcubierre drive actually required, the numbers came back catastrophic. The original estimates indicated that creating a warp bubble large enough to contain a spacecraft would require an amount of exotic energy equivalent to converting the entire mass of Jupiter, not the energy output of Jupiter, the entire mass of the planet, turned into exotic energy. Jupiter has a mass of about 1.9 times 10 to the 27th kilograms. That's roughly 318 times the mass of Earth. You would need to convert all of that into exotic matter with negative energy density just to move one spacecraft from one place to another. Think about what that means. Jupiter is not a small rock. It's a planet so large that all the other planets in the solar system could fit inside it with room to spare. Its volume is about 1,300 times larger than Earth's, and the Alcubierre drive, in its original form, would consume the mass energy equivalent of that entire planet as its fuel source. Not a fuel source you could refine or manufacture in a laboratory. An amount of exotic matter that dwarfs every human engineering project in history, by factors that don't fit in normal comprehension. Some physicists looked at those numbers and concluded the conversation was over. Beautiful mathematics, they said, completely unphysical. A solution that exists in the equations the way a frictionless surface exists in introductory physics, useful for learning, irrelevant to the real world. But other physicists kept going. The question they were asking was specific. Were those catastrophic energy requirements fundamental to the physics, or were they an artifact of Alcubierre's particular geometry? Could you design a different warp bubble, change the shape, change the thickness of the walls, change the configuration of the space-time curvature, and get the same effect with less exotic matter? Or could you find a way to replace exotic matter entirely with something that actually exists? Those questions didn't have obvious answers in 1994. They still don't have complete answers now, but the fact that they were worth asking at all kept the field alive through 2 decades where progress was slow and results were hard to come by. Researchers would publish papers narrowing the energy estimates, finding configurations that required less exotic matter, asking whether quantum effects might produce it in usable quantities at the right scales. None of those papers solved the problem, but they chipped away at it. They established that the energy requirements weren't necessarily fixed at Jupiter mass forever. They were a function of the geometry, and geometry is something you can optimize. For years after Alcubierre's paper, the warp drive lived in a kind of physics purgatory, too mathematically rigorous to dismiss, too physically impossible to build, until a series of papers beginning in the early 2020s started asking whether the energy problem was as hopeless as it appeared. For about 20 years after Alcubierre's paper, warp drive research made slow progress. Physicists could refine the mathematics, but the energy requirements stayed in the realm of complete fantasy. The problem wasn't that nobody was working on it. Physicists kept returning to the equations. They kept probing the geometry, testing the assumptions, looking for errors or shortcuts in the math. But every time someone ran the numbers, the answer came back the same. You needed exotic matter. You needed it in quantities that didn't exist anywhere in the observable universe. The original Alcubierre estimates placed the required energy at something equivalent to the entire mass of Jupiter converted into exotic negative energy, not a nuclear bomb, not a power station, not even the output of a star, the mass of Jupiter. That's roughly 318 times the mass of Earth. You'd need all of it, converted completely, just to generate the warp field for one spacecraft. For most physicists, that was close enough to impossible that the drive stayed interesting as mathematics and useless as engineering. Yet what most failed to grasp is the energy requirement isn't actually fixed. It depends on the geometry of the warp bubble. And around 2012, a physicist named Harold White, working at NASA's Johnson Space Center, started asking whether anyone had really optimized that geometry. What he found was striking. The original Alcubierre design used a warp bubble with a specific shape, essentially a thick, uniform shell of space-time distortion surrounding the spacecraft. White noticed that if you made the bubble wall thinner and oscillated the intensity of the warp field rather than holding it constant, the energy requirement didn't just drop a little, it dropped catastrophically. His revised calculations suggested the requirement could fall from Jupiter mass scale to something closer to the mass of a small spacecraft. That's not a marginal improvement. That's the difference between physically conceivable and physically inconceivable. While Alcubierre was working out the mathematics of warp bubbles, the other major theoretical shortcut through spacetime had been sitting in the physics literature since 1935. That year, Albert Einstein and his colleague Nathan Rosen published a paper describing something strange embedded in the equations of general relativity. The math permitted a kind of tunnel, a bridge connecting two separate regions of space-time. Not a path through space, a path that sidesteps space entirely. Physicists call these Einstein-Rosen bridges. Most people call them wormholes. Here's the simplest way to picture it. Imagine the universe as a flat sheet of paper. 2 points on opposite ends of that sheet are separated by a long distance. Travel between them normally, and you trace a long curve across the surface. But fold the paper so those 2 points touch, punch a hole through, and suddenly those distant locations are directly connected. A wormhole does exactly that, except the sheet is space-time itself, and the fold is real curvature produced by gravity. The geometry is strange, but the math is not wrong. General relativity permits these structures. That's not a casual claim. The same equations that correctly predicted gravitational waves, black holes, and the bending of light around massive objects also permit wormhole solutions. They emerge from the theory the same way Alcubierre's warp bubble does, not as approximations or loose analogies, but as exact solutions. The universe's own equations say these things can exist. But here's what the equations also say. An Einstein-Rosen bridge, left to itself, doesn't stay open. It collapses almost immediately. Not slowly, not gradually. The throat of the wormhole pinches shut before anything, light included, could pass through it. The original Einstein-Rosen solution described a wormhole that was geometrically possible, but physically useless. You can't traverse something that closes before you take a single step. The question physicists spent decades wrestling with was whether a traversable wormhole was theoretically possible. Could you hold the throat open? In 1988, physicists Kip Thorne and Michael Morris published a serious analysis of exactly this problem. Their conclusion was cautious but remarkable. A traversable wormhole was theoretically possible, but keeping it open required exotic matter, material with negative energy density. The same thing the Alcubierre drive needs. Not antimatter, not dark matter. Something with a negative energy density that pushes space-time outward rather than curving it inward. That requirement is where both ideas run into the same wall. Exotic matter in the quantities needed to hold open a traversable wormhole has never been observed. The Casimir effect produces tiny regions of negative energy density between closely spaced metal plates in a vacuum. The amount of negative energy involved is so small it barely registers. Scaling that up to hold open a wormhole throat large enough for a spacecraft would require quantities of exotic matter that may simply not exist in the universe in any accessible form. The size problem is worth sitting with. A traversable wormhole throat stable enough to pass a human through would need to be held open against enormous gravitational pressure. The exotic matter required isn't a small engineering challenge. The numbers are comparable to those for warp drives, extreme in ways that strain any meaningful comparison to existing technology. Now, something more recent has entered this picture, and it's genuinely strange. Juan Maldacena is one of the most cited physicists alive. In 2013, he and Leonard Susskind proposed something that physicists are still working through. The idea that wormholes and quantum entanglement might be the same phenomenon described in different languages. They called it ER equals EPR. ER refers to Einstein-Rosen bridges, wormholes. EPR refers to Einstein, Podolsky, and Rosen, the three physicists who first formally described quantum entanglement in 1935, the same year Einstein and Rosen published their wormhole paper. The proposal is this: when two particles become quantum entangled, they may be connected by a microscopic wormhole, not metaphorically, literally. The non-local connection that entanglement creates between particles might be the geometric connection of a tiny Einstein-Rosen bridge stretched across space-time. The bridge isn't traversable. You can't send information through it. And it doesn't violate what we said earlier about entanglement and communication, but the underlying geometry might be real. This is speculative. Nobody has proven it, but it's attracted serious attention from serious physicists, because if ER equals EPR is correct, it suggests something deep, that quantum mechanics and general relativity, the two great frameworks of modern physics that have resisted unification for a century, might be connected at a level nobody had previously seen. Wormholes and entanglement might not be separate phenomena. They might be two faces of the same structure. That doesn't immediately help anyone build a traversable wormhole, but it changes the way physicists think about what wormholes are. There's still the causality problem. Traversable wormholes, like warp drives, could theoretically create what physicists call closed time-like curves, paths through space-time that loop back to their own starting point in time. Travel through a wormhole, connect 2 points in space, and under certain configurations, you could find yourself arriving before you left, not as a figure of speech, as a mathematical consequence of the geometry. Stephen Hawking spent years arguing that nature prevents this. He called it the chronology protection conjecture, the idea that the laws of physics conspire to prevent closed time-like curves from forming, that quantum effects would destabilize any structure that threatened to create a time loop before it could become traversable. It's an elegant idea. The universe, in this view, enforces its own consistency, but the chronology protection conjecture is not proven. It's a conjecture. Hawking believed it was almost certainly true. Many physicists agree with him. Others are less sure. We don't currently have a theory that fully unifies quantum mechanics and gravity, and that gap may be exactly where the answer lives. What we can say is this: wormholes are permitted by general relativity. They require exotic matter to stay open. They face causality problems that are not fully resolved. The theoretical machinery around them has grown more sophisticated in recent years, particularly through the ER equals EPR connection. And they remain, like warp drives, in a region of physics where the mathematics is real, but the physical path from equations to engineering has not been found. Wormholes and warp drives share the same fundamental physics problems: exotic matter, causality violations, energy requirements, and they may share something else. They may both be either impossible for reasons we haven't fully articulated, or possible in ways that no civilization will ever have the engineering capability to exploit. There's a problem with faster-than-light travel that goes much deeper than engineering, deeper than exotic matter, deeper than energy requirements. It lives in the structure of space-time itself, and once you see it, you can't unsee it. Here's what most people don't realize. Special relativity doesn't just change how fast things move. It changes what "at the same time" even means. Two events that appear perfectly simultaneous to one observer will appear to happen in different orders to another observer moving at a different velocity. This isn't a trick of perception. It isn't a measurement error. It is a fundamental feature of how the universe is built. Simultaneity is not absolute. It depends on your reference frame. That sounds abstract, but it has a concrete and deeply uncomfortable consequence when you combine it with faster-than-light travel. If you can send a signal faster than light, you can, under certain carefully constructed conditions, send that signal into the past. Not metaphorically into the past, causally into the past. The signal arrives before it was sent, as measured by a different observer moving at a different velocity. The math is real. The geometry of space-time makes this possible the moment you allow faster-than-light communication. Think about what that means. Physicists constructed a thought experiment to make this concrete. It's called the tachyonic anti-telephone. Person A sends an FTL message to person B. Because of the relativity of simultaneity, person B can transmit a reply, also faster than light, that arrives back at person A before A sent the original message. Person A receives the reply. Then A decides not to send the message in the first place. But if A never sent the message, B never received it. And if B never received it, B never sent the reply. And if B never sent the reply, A never received it, and A has no reason not to send the original. The contradiction is complete. The logic collapses. This is not a paradox about stepping on butterflies. It's a direct contradiction embedded in the causal structure of the universe. Cause precedes effect. That's not a philosophical preference. That's how physics works, everywhere, in every experiment ever conducted. Faster-than-light signaling breaks this at the level of the equations. So what do you do with that? Physicists have proposed several ways to wrestle with the problem. The most serious one is called the Novikov self-consistency principle. The idea is that the past is fixed. It cannot be changed. Closed time-like curves, the technical name for these loops back through time, can only form if everything that happens inside them is already consistent with what happened before. You can't go back and prevent your own birth. You can't send a message that contradicts its own origin. The universe simply won't permit solutions that generate contradictions. Only self-consistent histories are physically allowed. It's a coherent framework. The mathematics supports it, and it resolves the grandfather paradox and the tachyonic antitelephone in a single stroke. But it raises an equally uncomfortable question. If only self-consistent solutions are allowed, then the future is in some sense already determined. You can travel through a closed, time-like curve, but you can't change anything. Every choice you make was already made. That's not really a resolution. That's a different problem wearing a resolution's clothes. Stephen Hawking had a different answer. He proposed what he called the chronology protection conjecture. The idea is that quantum effects, specifically the behavior of quantum vacuum fluctuations near a closed time-like curve, would always act to prevent such structures from forming in the first place. The universe protects its own history, not through logic, but through physics. Every time spacetime geometry approached the conditions needed to create a closed time-like curve, quantum radiation would build up and destroy the structure before the loop could close. Hawking was clear that this was a conjecture. He couldn't prove it. Nobody has proven it since. We don't have a complete theory of quantum gravity, which is exactly what you'd need to know for certain whether Hawking's protection mechanism actually works. So we have two proposed resolutions, and we can't fully verify either of them. What we do know is this. Every scheme that allows genuine faster-than-light signaling carries this problem with it. Tachyons carry it. Certain wormhole configurations carry it. The original Alcubierre drive, operated at superluminal speeds, carries it. The causality issue isn't a side note. It sits at the center of every serious objection to faster-than-light travel. But here's the thing. The causality problem specifically arises from travel or communication that exceeds light speed in a way that connects events across space-like intervals. Subluminal warp drives, ones that move faster than conventional spacecraft but stop short of light speed itself, don't generate closed time-like curves. They don't allow the tachyonic antitelephone. They don't break causality in any form we can identify. They just move very fast. Fast enough to cross interstellar distances in years rather than millennia. Fast enough to be genuinely transformative without opening any of the logical trapdoors that superluminal travel carries. The physicists who have spent the last decade working on warp drive theory are not naive about this, which is why the most serious recent work has pivoted towards subliminal designs that avoid the causality minefield entirely, while still offering something genuinely useful. A path between the stars that doesn't require thousands of years. Let's put aside the physics for a moment and think about what it would actually mean if any of this worked. The nearest star to our Sun is Alpha Centauri. It sits about 4.37 light-years away. That sounds like a tidy number until you translate it into something real. The Parker Solar Probe is the fastest spacecraft humanity has ever built. It travels at roughly 430,000 miles per hour. That's fast enough to circle the entire Earth in about 3.5 minutes. And at that speed, reaching Alpha Centauri would take approximately 6,300 years. Not generations, Civilizations. The Roman Empire rose and collapsed in less time than that. Written language is only about 5,000 years old. We are talking about a journey so long that every human institution, every language, every form of government we have ever known would have time to be born, flourish, and disappear before the spacecraft arrived. Here's what most people don't realize. Alpha Centauri is our neighbor. It's the closest thing to our solar system in the entire galaxy. If the Milky Way were a continent, Alpha Centauri would be the house next door. And we can't get there, not in any meaningful human sense. The Milky Way itself is about 100,000 light-years across. That number is almost impossible to sit with. Even if you could somehow travel at 1% of the speed of light, a velocity that would require engineering we don't currently possess, it would still take 437 years to reach Alpha Centauri. Nearly 5 centuries at 1% light speed just to reach the nearest star. At 10% of light speed, which would represent an achievement so far beyond our current capability that no serious timeline exists for approaching it, the journey would take 43 years, one human lifetime, to reach one star, and the galaxy contains somewhere between 200 and 400 billion of them. Without faster-than-light travel, humanity is not just limited in where it can go, it is permanently confined, not temporarily. Not until we build better rockets. Permanently. The physics does not improve with engineering. The distances are what they are, and the speed of light is what it is. A civilization that never solves the FTL problem will live and die in its home system, no matter how advanced it becomes in every other respect. This brings up something called the Fermi paradox. The physicist Enrico Fermi asked a simple question. Given how old and large the universe is, and given how many stars there are, where is everyone? If intelligent life is even moderately common, there should be civilizations far older than ours. Some should be millions of years ahead of us technologically, and yet we see no evidence of anyone. The universe appears empty in a way that's genuinely difficult to explain if interstellar travel is straightforward. One answer is this. Maybe interstellar travel is simply too hard. Maybe the speed of light is not a barrier that any civilization can overcome, no matter how advanced. Maybe every intelligent species that has ever existed is sitting on its home planet or inside its home system, looking at the same stars we look at, asking the same questions we ask, and going nowhere. The galaxy might be full of civilizations that are each permanently isolated by the same wall we're staring at. That's a strange kind of loneliness. Billions of minds scattered across 100,000 light-years, each unable to reach any of the others. But flip it around. If faster-than-light travel is possible, if any version of a warp drive could actually be built, the calculus changes entirely. A galaxy with FTL is a completely different place from a galaxy without it. Civilizations could spread, they could encounter each other, they could trade, compete, form alliances, or go to war. The history of our own planet suggests that when previously isolated populations make contact, the results are transformative in every direction, culturally, biologically, technologically. Scale that to interstellar civilizations, and the implications go beyond anything we can usefully predict. There's something else worth considering. Every element essential to life as we know it, carbon, oxygen, nitrogen, iron, calcium, was forged inside stellar cores. Stars fuse lighter elements into heavier ones over millions and billions of years, then scatter those elements across space when they die. The iron in your blood was made inside a dying star. The calcium in your bones came from the same process. The oxygen you're breathing right now was manufactured in stellar interiors and released into the galaxy by ancient supernovae. Those same processes are happening throughout the Milky Way right now. There is no reason to think our solar system is the only place where scattered stellar material gathered into a rocky planet at the right distance from the right kind of star. The chemistry that produced life here is not exotic. It's universal. We've confirmed thousands of exoplanets. Dozens sit inside the habitable zones of their stars. Estimates suggest there may be billions of Earth-like worlds in the Milky Way alone. The question of whether any of them host life, whether anything living has ever looked up at the sky from another world, is one of the most profound questions any mind has ever asked. And the honest answer is that we have no idea. We can't get there to check. We can detect the atmospheres of some nearby planets with telescopes, and we can look for chemical signatures that suggest biological processes. But to actually know, to resolve the question in any definitive sense, requires closing the distance. That's what faster-than-light travel actually means for humanity. It's not about convenience or speed. It's about whether we ever get to answer the question. Every star we can see in the night sky is a sun. Many of those suns have planets. Some of those planets may have oceans. Some may have continents. Some may have something living on them. And without a way to cross the distance, all of that is permanently out of reach, visible and forever inaccessible, like a photograph of something you can never touch. The Fermi paradox cuts in both directions. If no civilization ever solves the FTL problem, then the galaxy might be populated and silent simultaneously. But if someone solved it, we might find out we've had neighbors the entire time. Without faster-than-light travel, we will never know whether we are alone in the universe. The distances are simply too vast. And even if a signal from another civilization crossed the galaxy toward us tonight, the civilization that sent it might be extinct by the time we had a conversation with their descendants. Our universe is 93 billion light-years across, and that number is so large it barely qualifies as information. Our brains didn't evolve to process it any more than they evolved to intuitively grasp the interior of a red supergiant star. Let's try to make it real. The observable universe contains an estimated 2 trillion galaxies. Not 2 trillion stars, 2 trillion galaxies. Each of those galaxies holds hundreds of billions of stars on average. Some hold trillions. The Milky Way alone contains somewhere between 100 and 400 billion stars. And it is an ordinary spiral galaxy, unremarkable by cosmic standards, sitting in a quiet corner of a modest galaxy cluster. There is nothing special about our address in the universe. We are not near the center of anything. We are not in a particularly dense region of space. We are just here, on a medium-sized planet, orbiting a medium-sized star, in one of 2 trillion galaxies distributed across 93 billion light-years of space. And the speed limit across all of that is 299,792 kilometers per second. Think about what that asymmetry means. The universe appears to have been built at a scale that is almost perfectly calibrated to be out of reach. To cross our own galaxy from one side to the other at the speed of light would take 100,000 years. Not a long human lifetime, not a dynasty, not a civilization. 100,000 years. The earliest anatomically modern humans walked the Earth roughly 300,000 years ago. To cross the Milky Way at light speed, you would need a third of that entire span of human existence, traveling at the fastest speed physics permits, just to get from one side of our galaxy to the other. And the Milky Way is one galaxy out of 2 trillion. Here's what makes this even harder to sit with. The universe is not empty. It is not a vast cold void with a few rare islands of matter scattered impossibly far apart. It is filled with the conditions that produced us. Water is one of the most common molecules in space. Carbon chemistry, the foundation of every living thing we have ever found, is distributed throughout the galaxy in molecular clouds, in planetary atmospheres, in the ice on comets. The raw materials for biology are not rare, they are everywhere. We have now confirmed the existence of thousands of exoplanets. Thousands. And that number represents only what we found in a tiny fraction of the galaxy using instruments that have been operating for a relatively short time. When astronomers look at the data and extrapolate, the estimates are staggering. There may be tens of billions of rocky planets in the Milky Way orbiting in the habitable zones of their stars. Some estimates push higher than that. Dozens of confirmed exoplanets already sit in the range of distances from their stars where liquid water could exist on a surface. Liquid water. The one thing we know, without exception, is required for life as we understand it. The universe is enormous and apparently full of the right conditions, and we are sitting here, unable to reach any of it. Voyager 1 launched in 1977. It has been traveling continuously for nearly 50 years, accelerating away from Earth on a trajectory that carried it past Jupiter, past Saturn, past the outer planets, and eventually out past the heliopause, the boundary where the sun's influence gives way to interstellar space. It is, right now, the most distant human-made object ever built. Its current distance from the sun is roughly 24 billion kilometers. That sounds like a long way. It is a long way by any human scale. The nearest star to our sun is Proxima Centauri, part of the Alpha Centauri system, sitting about 4.24 light-years away. That distance in kilometers is approximately 40 trillion kilometers. Voyager 1, after nearly 50 years of continuous travel, has covered about 24 billion kilometers. The distance to the nearest star is roughly 6,300 times farther than Voyager has traveled in half a century. Let that settle for a moment. 6,300 times farther. If Voyager were somehow aimed directly at Proxima Centauri and maintained its current speed, it would arrive in approximately 73,000 years. And Proxima Centauri is our closest neighbor. It is the star next door. Beyond it, the distances grow larger by factors that make even this comparison feel modest. This is the trap. The universe hands you a galaxy filled with billions of potentially habitable worlds, a chemistry that suggests life could be widespread, and a set of physical laws that make visiting any of it essentially impossible. You can look, you can detect, you can measure atmospheres from 40 light-years away, using instruments sensitive enough to detect a single molecule's spectral fingerprint. But you cannot go. Not with any technology that operates within the speed of light. Not in any time frame that a civilization could sustain. There's an uncomfortable thought buried in here. The Fermi paradox asks why, given the apparent abundance of potentially life-supporting worlds, we see no evidence of other civilizations. One answer is simply this. The trap is universal. Every civilization that has ever existed, no matter how advanced, runs into the same speed limit, the same 100,000-year crossing time for its own galaxy, the same 4-light-year gap to its nearest stellar neighbor. Intelligence might be common, the will to explore might be universal, and the universe still says no, unless there is something in the equations, some configuration of space-time geometry, some way of moving space rather than moving through it, that changes the calculation. Not for every civilization, not easily, not cheaply, but in principle, just in principle. That's why the Alcubierre mathematics matter. That's why the 2026 phase singularity measurement matters, even with all the caveats attached to it. That's why researchers are publishing papers about warp bubbles and subluminal drives and exotic matter alternatives. Because the alternative to finding a way through this problem is accepting that the universe is essentially a display case. 2 trillion galaxies, billions of potentially living worlds, and a species on one small planet that can see it all and touch none of it. We built the Parker Solar Probe and the Voyager spacecraft and every satellite that has ever left Earth, and collectively they've barely scratched the surface of our own solar system, which means the question of whether faster-than-light travel is possible is not an idle curiosity. It is the question that determines whether humanity ever becomes anything more than a civilization living and dying in one small corner of one ordinary galaxy. The question of whether faster-than-light travel is possible won't be settled in a lab next year, and anyone who tells you otherwise is selling something. But that doesn't mean the research is standing still. It isn't. The field has more serious momentum behind it right now than at any point in the last 30 years, and several developments are pointing toward experiments that could actually test pieces of this physics rather than just theorize about it. One of the most significant tools on the horizon is gravitational wave detection. LIGO, the Laser Interferometer Gravitational Wave Observatory, can already detect ripples in spacetime smaller than a fraction of a proton. That sensitivity is almost incomprehensible. If a warp bubble were to form and then collapse, even at a tiny scale, the spacetime distortion involved should produce a gravitational wave signature. Researchers have started working out what that signature would look like. They're asking whether it would be distinctive enough to separate from other sources. Nobody has detected one, but the fact that we can even frame that as a search target is new. 10 years ago, we hadn't directly detected gravitational waves at all. Now we're asking whether they could reveal evidence of spacetime engineering. There's a parallel track happening at much smaller scales. Some physicists have proposed tabletop experiments, not spacecraft, not massive particle accelerators, but precision laboratory setups that could probe the physics of space-time curvature in controlled conditions. The idea is to test whether certain configurations of electromagnetic fields can produce measurable effects on local space-time geometry. These aren't warp drives, they're tests of the underlying principles that warp drive theory depends on. If the principles don't hold, you know the theory has a problem. If they do, you've confirmed something real. That's how physics is supposed to work. The James Webb Space Telescope is contributing to this picture in a different way. Webb wasn't built to study warp drives. It was built to study the early universe, galaxy formation, and planetary atmospheres. But the picture it's building has a direct bearing on the motivation to solve the FTL problem. Webb has already detected atmospheric signatures on planets orbiting other stars. It's found evidence of carbon-bearing molecules in the atmospheres of worlds we couldn't study in any detail a decade ago. Every discovery it makes about planetary atmospheres deepens the case that the conditions for life are not rare. Billions of potentially habitable worlds in the Milky Way alone. That's the context in which FTL research is happening. The more life-supporting environments we find, the more urgent the question becomes. Here's what most people don't realize about how physics actually advances. It doesn't advance by confirming what we already expect. It advances when an experiment contradicts the theory. Quantum mechanics wasn't built by philosophers sitting in rooms imagining it into existence. It was forced on physicists by measurements that didn't make sense under classical physics. Black holes were considered a mathematical oddity for decades, a solution to Einstein's equations that probably didn't reflect reality. Then we imaged one. Gravitational waves were predicted in 1916. We detected them in 2015. Nearly a century of waiting. The pattern keeps repeating. The universe has a habit of turning theoretical curiosities into physical realities. Warp drive research could follow that same arc. The causality problems might be insurmountable. Exotic matter might not exist in the quantities needed. The revised energy calculations might fall apart under more rigorous scrutiny. All of that is possible, but it's also possible that the next generation of physicists finds an approach we haven't thought of yet, a way of threading all the needles at once, combining insights from quantum gravity, electromagnetic field manipulation, and the new geometry of spacetime that the revised warp models have opened up. Physics has been surprised before. It will be surprised again. What drives the research forward isn't certainty. It's the recognition that the edges of rules are where discoveries live. Every time someone has pushed hard against a physical boundary, not ignoring it, not pretending it doesn't exist, but studying it carefully, mapping exactly where it applies and exactly where it doesn't, something unexpected has emerged. The 2026 Singularity experiment is a recent example. It didn't break relativity. It mapped a boundary with precision nobody had achieved before. That's what serious physics looks like. Not a headline, a boundary, precisely drawn. The warp drive might be impossible. The wormhole might be impossible. Tachyons might be permanently confined to the mathematics, but the researchers publishing today are not the last word on any of this. There will be physicists working on this problem 50 years from now who have tools we cannot imagine and knowledge we haven't built yet. We might be decades from a breakthrough, we might be centuries away, or we might be right at the edge of figuring out something that changes the trajectory of everything. And the honest answer is that nobody knows, which is exactly what makes this the most interesting problem in physics. We started tonight with a headline, and by now you know that the headline meant something more complicated than it sounded. Something did move faster than light. The measurement was real, the numbers were confirmed, and yet no spacecraft is being designed. No warp bubble was created. No message was sent backward through time. What moved faster than light was a dark point inside a wave, a geometric feature, not a physical object, and it lasted for 3 quadrillionths of a second inside a material thinner than a single human hair. That is the actual discovery. And here's what most people don't realize. That distinction doesn't make it small, it makes it precise. Throughout humanity's past, the stars appeared as nothing but lights, points of brightness in the dark. Nobody understood they were other suns, separated from us by distances so vast that the light reaching your eyes tonight left those stars before our species existed. Nobody knew the galaxy was a structure. Nobody knew that the carbon in your body was assembled inside a dying star, expelled in a supernova, scattered across space, and eventually gathered by gravity into a planet, and then into you. We've figured all of that out in roughly the last 100 years. Not thousands of years, not a millennium. 1 century. In that same century, we went from the first powered aircraft to probes that have left the solar system entirely. We built instruments sensitive enough to detect a ripple in spacetime from 2 black holes colliding 1 billion light-years away. We pointed a telescope at a shadow and produced an image of a black hole. We confirmed the predictions of quantum mechanics to a precision that exceeds anything else in the history of science. The universe is 13.8 billion years old. We have been doing modern physics for about 120 of those years. If you compressed the history of the universe into a single calendar year, all of human science would occupy the final fraction of the final second of December 31st. We are not a mature civilization looking back on completed knowledge. We are a young species that has barely begun. We don't know if faster-than-light travel is possible. The causality problems are real. The exotic matter problem is real. The energy requirements are real. But the Alcubierre warp drive was considered pure fantasy in 1994. And by 2025, serious physicists were publishing peer-reviewed papers suggesting the energy requirement had dropped from the mass of Jupiter to the equivalent of 1 ton of TNT. That is a shift that tells you the problem is not fully understood yet, and problems that aren't fully understood can still be solved. Think about what that means. Every piece of physics we now take for granted was once a question nobody knew how to answer. The constancy of light speed was a puzzle before Einstein. Black holes were a mathematical curiosity before we detected one. Gravitational waves were a theoretical prediction for 100 years before LIGO heard them. The universe does not run out of answers. It runs out of the questions we haven't thought to ask yet. The measurement made in 2026, dark points inside a hexagonal boron nitride lattice, moving faster than light for 3 quadrillionths of a second, is not the answer to whether humanity will ever reach another star. It isn't even close to that answer. But it confirms something that had been predicted for 50 years without proof. It gave physicists a new tool, a real experimental technique, a way of studying wave behavior at scales and speeds that were previously invisible to us. That is how physics works. You confirm the small prediction and it opens a door to a larger one. In physics, every measurement is a clue, and somewhere in what we've just explored tonight, in the superluminal geometry of wave singularities, in the space-time mathematics of warp fields, in the experimental work of researchers who believed questions worth asking were worth answering. There is something pointing forward, and we just can't see quite yet where it goes.